Hello, and welcome to Team 1042's analysis on Problem A, Kangaroo Care, in the Semi-ODE 2023 competition. Our team consists of myself, Micah, and my colleagues Otto and Michael. We are undergrads attending Colorado State University with our professor Matt Kipper as our coach. Now, let's dive into Kangaroo Care. For our model, it is solely based around the idea of kangaroo motherly care, which observes how an infant's survival or mortality rate can change due to the immediate safekeeping from a mother. By safekeeping, I mean one of three things. Care after birth, which is the amount of time that the mother cares for the infant in the first 24 hours immediately after birth. Frequency of care, which in our case is between 8 to 16 hours that the mother can provide for the infant. And lastly is quality of care. These three nursing terms depend heavily on the mother's utilization of her own resources, stress, and time to drive infant survival, while battling outside natural issues such as infection, predatorial death, and resource scarcity that drive infant mortality. However, we're able to assume that predators and limited resources aren't a threat, allowing us to simplify our model to be based upon motherly care and infection. As for care, we're assuming that there's an even distribution of care across all mother and infant pairs, as well as a constant care frequency over our 28-day model. As for infection, we're assuming climate and weather aren't contributing to hypothermia or any unexpected death, leaving severe infection as our only outside issue. Now, let's move on to defining our care terms. For care frequency, we created a Heaviside function to account for skipping days of care, in which the difference between our day number and the end of our skipped care interval will either produce a care frequency term, which is a percentage of the day being used by the mother to nourish the infant, or simply be zero for no care at all. And if you can see, we can relate this frequency of care term to our quality of care term, which, if we start at the bare minimum, 8 hours, our stress will be 0, allowing our quality of care to be 1. But as we increase our frequency of care, our stress will be increased, and therefore our quality of care will be decreased. As for our care after birth term, we see no correlation between our quality of care and frequency of care. It's simply just based upon the amount of time the mother provides in the first 24 hours after birth. As for infection, we can see our infection of hypothermia is equal to 0, and our infection of severe infection / sepsis is equal to 0.2, which is the probability that these kangaroos will get infected and lead to a lower decreased health, which leads us to our health equation.
The health equation is a culmination of three main contributions. The first contribution is based off the quality of care and the frequency of care. As the frequency increases, it can have a positive contribution to this term. However, that can also increase stress, which will cause the quality of care, Q sub C, to depreciate to 0. So that there is a specific maximum between these two that can have a positive contribution to overall population health. The next term is going to be our infection term, which is our risk of infection times time, which is just going to add a negative contribution to the overall health or and the health change, and is offset by these positive contributors, which really just plays into our model where if these populations are not getting the frequency as well as the time after birth care that they need, that their risk of infection is going to decrease their health accordingly. The third term, as I kind of mentioned, is the time after birth care, or T sub S, and the three main variables in this term are going to be K, which is a arbitrary constant and a scaling factor, as well as T, because our effect changes in time and over time, and as well as 1 minus TS, which is going to signify that from our initial given problem that when the infants have more than 24 hours before they start their care regimen with the care frequency, that there's going to be a negative contribution to their total health. However, if they are receiving care under 24 hours, it's going to have a positive contribution to their health because T sub S is in terms of days, so 24 hours will be 1 whole day. Our next equation is going to be our mortality rate, or our mortality risk equation, and we just have a differential of dm dt is equal to c times h, where c is a scaling factor and h is the health of the population. And this equation only highlights that essentially that the risk of death, or dmtt, is going to be linearly proportional to the health of our population. For our population equation, we derived it given a simplified closed system differential for similar to like a material balance where you have dp dt is equal to the rate in minus rate out. And we can simplify it because the rate in is going to be 0 as no population is born, as well as no kangaroos are coming into the system. And as well, our rate out will be completely dependent on mortality because no kangaroos will leave the system alive, and so they only converted from living kangaroos to dead. And if you multiply both sides by dt to separate the equation and integrate both sides by their respective differentials or their derivatives, then you get the equation below where you have population is equal to the starting population minus the definite integral of the mortality risk in terms of time, and where your starting population is going to be your constant of integration. And so then we've got our total population is equal to our starting population subtracted by our total death count over the time interval, where our starting population is going to be 100 kangaroo pairs and m sub t is mortality at each point in time. One can solve this solution ODE when you take the equation from the previous slide, p is equal to p naught minus negative integration of mortality risk dt, and plug in the health equation and c for mortality risk from the previous slides, as well as your initial condition of 100 kangaroo pairs. And when you plug in and integrate indefinitely, you get this equation. And then for our case scenario and what we're calculating, these are our scaling factors of c equals 5 and k equals 1. And of course, we're going to be graphing our data on an interval of 0 to 28 days because that was the length of the study in the problem statement.
Moving on, we have our health solution graphs with frequency of care of 10 hours, 12 hours, and 14 hours. As time increases, the health decreases to a steady point of health, and as the hours increase for frequency of care, the health decreases due to the mother's stress. The next graph we have is the mortality solutions for the same frequency of care hours. And as we decrease frequency of care, the mortality rate increases due to less time with their mother. In our next graph, we have our population solutions for the same frequency of cares, and as the hours decrease for frequency of care, the population decreases as well because of a higher mortality rate.
In this solution, we highlighted how skipping every 5th day would affect the overall infant health over the total interval of 28 days. In this solution, you can see where the heaviside step function came into play when the remainder was 0 on intervals of 5, and so that care was stopped on every 5th day. You can see that infant health dramatically decreased when care was skipped, and that overall, holistically, this would not be good for the infant care. However, that the infant did spring back to their perceived health drop over time, which is consistent with the same graph but without skipping the 5th day. So, in a model that considered resource distribution, overall, the health plateau did not decrease at all with these spikes. However, the considerations of what these changes in health over time, rapidly every 5th day, would affect the overall infant health in another model. Applications and limits. The most clear application for this model is obviously for kangaroo care and habitation facilities, as using this model could help them provide better care to their populations, decreasing infant mortality, as well as allowing them to rehabilitate these animals and send them into the wild, or keep them domestically but healthy. Additionally, this care plan can also be adapted for other captive non-domesticated animals, just with sample data or scaling factors to adjust how that these animals may have different needs as well as different impacts on certain variables. As well as KMC models for preterm infants requiring pediatric and home care is a potential application, as that kangaroo mother care has also been very important in preterm infants who need more care and allows them to increase their birth weight due to a variety of factors, as well as have a decreased rate of infection and increased neurological development. And so while other factors have to be considered and further models to be explored, that is a potential application for these types of population models. Some limits of this model is that the main variables that were taken into account and expressed were care frequency, interval, stress, infection, and mortality, which were the main things considered. However, it would be interesting to maybe consider, for instance, resource distribution and limitation, as well as fitting our model to more experimental data. Some further steps that could be implemented in this model to further it would be as well as you could treat each kangaroo pair independently with independent health, risk of infection, as well as interactions between population points, whether they're physiological, psychological, or due to disease. The only resources utilized in this project was the paper given in the problem statement about kangaroo mother care, as well as OpenAI's ChatGPT for a predictive text model. Thank you for watching.